since we know that when an ionic compound is dissolved in water, it dissociates, it turns out that there's several ways we can write chemical equations. One is a molecular equation, showing that essentially when I think of a molecular equation, I think of everything together in the compounds and molecules. Okay, so in this example, potassium hydroxide is reacted with lead nitrate, producing potassium nitrate aqueous and a solid lead hydroxide. Okay, we know that there's really no KOH formula units in the aqueous solution. It has dissociated into potassium and hydroxide ions. Okay, so another way we can write a chemical equation instead of everything together in molecular equations is what's known as the complete ionic equation, where we break up any aqueous species that has dissociated or ionized into its corresponding ions. So potassium hydroxide aqueous really means we have potassium and hydroxide. Lead nitrate aqueous really means that we have lead plus 2 and nitrate. Notice that we keep the coefficients needed to keep this chemical equation balanced. Well, potassium nitrate on the product side, it really is 2 moles of potassium cations and 2 moles of nitrate ions. Notice that we don't break up lead hydroxide because that is not an aqueous species. We're not lead hydroxide because it's not soluble, doesn't dissociate. Any species that's in the solid, liquid, or gas phase, we don't break up because, of course, they don't dissociate. If we look at the complete ionic equation, you can see that there are several ions that are the same on the left and right side of the equation, the same as the reactants as they are on the products. We refer to these as spectator ions. They really didn't do anything in the chemical equation, potassium as being one of them and nitrate being the other one. What really happened is that lead plus 2 and 2 moles of hydroxide ions formed lead hydroxide solid. Okay, it turns out that we could have added any soluble lead component to sodium hydroxide or magnesium hydroxide, and the potassium, sodium, or magnesium wouldn't have reacted. And so it doesn't matter how we got the hydroxides in solutions. All that matters is we got the hydroxides and the lead in solutions. Okay, if we remove all of the spectator ions, take those out, because again they could be any other counter ions, what we have is the net ionic equation. And this shows all of the reactants that actually reacted to produce a new chemical compound. In this case, it's only lead plus 2 and 2 moles of hydroxide, forming a lead hydroxide solid compound. Okay, so what we can do is take a look at these two chemical equations, write the complete molecular or complete ionic equations, and then remove the spectator ions to form the net ionic equation. So potassium sulfate really means that we have 2 moles of potassium plus 1 sulfate 2 minus polyatomic ion. Lead nitrate is 2 silver plus aqueous plus 2 nitrates. And they produce 2 moles of K plus aqueous again, and 2 nitrates plus our silver sulfate. That's a solid compound, and so that does not dissociate, so we just keep that the same. So this is our complete ionic equation. If we look through and find our spectator ions, potassium didn't do anything, and nitrate again didn't do anything, we can distill this down into our net ionic equation. 2 moles of silver aqueous plus 1 mole of sulfate aqueous produced our silver 2 sulfate solid compound. Okay, let's take a look at the next example. We've got sodium carbonate plus hydrochloric acid yields sodium chloride, carbon dioxide gas, and water. Okay, again, anytime we have an aqueous component, we can break that up into its to the complete ionic equation. See, this is 2 moles of sodium plus 1 mole of carbonate aqueous plus 2 H plus. This is an aqueous, so that must be an acid. H plus ions plus 2 chloride ions yields 2 sodium aqueous ions plus 2 Cl aqueous ions, and CO2 and water stay the same because they are not aqueous. Gas phase and water, they do not dissociate. Okay, so what we can do is we can take a look at sodium, spectator ion, and then the chloride was the spectator ion. So our net ionic equation would be 2 moles of H plus aqueous plus a CO3 2 minus ion, or carbonate ion, produces carbon dioxide gas and water. Now the title of this unit is, of course, acids and bases, and so we had to figure out a little bit more about ionic equations, and now we can discuss our acid-base reactions. Remember, when we named acids, anytime you produce a H plus ion in solution, which is the definition, Arrhenius definition of acids, or if you donate a proton to form H3O plus hydronium ion, the Bronsted-Lowry definition of acids, that is the definition or definitions of an acid. So anytime you see H plus or H3O plus, the hydronium ion, what you're referring to is an acid compound or molecule. Any base that forms hydroxide ions is our base. So any soluble hydroxide ionic compounds, and then of course any molecule that can accept a proton off of water, such as ammonia, is known as a base. So NH3 plus water. Turns out nitrogen has that lone pair of electrons, so it can accept a proton from water, and it sets up an equilibrium with the NH4 plus ion, ammonium ion, and hydroxide. So that's how ammonia is classified as a base, because of the fact that it produces a hydroxide in solution because it can accept a hydrogen off of the water molecule.